Hello everyone. In this video we will learn about the Feynman diagram. And Feynman diagram is a visual tool to understand the interaction of particle. Remembering the equations such as the alpha decay, beta decay, or the interaction of one electron with another electron may be slightly complex. And as a human being, we are good at remembering the images. So these diagrams represent the interaction of particle in a simple way. To understand the Feynman diagram, we have to know the type of forces in nature. So let me write the name of the topic, Feynman diagram. So to understand the Feynman diagram, we should know the types of forces in nature. So there are four fundamental forces in nature. And these four fundamental forces are: first one, strong nuclear force. So as the name suggests, this one is the strongest force in the nature, though it is a short range. Second one, weak nuclear force. Third one, electromagnetic force. And the fourth one is the gravitational force. The strongest force in nature is the strong nuclear force, strongest but short range. And what is the order of the range? About 1 Fermi. It means the range is about 10 power minus 15 meter. This force is responsible for holding the proton and neutron within nucleus. So the role of strong nuclear force is to hold the proton and neutron within the nucleus. Next one, the weak nuclear force. It's responsible for decay or responsible for decays. Electromagnetic force, long range, and acts between charges. Gravitational force, again long range, weakest force in nature. It's the weakest force in nature, but because it acts between the masses, and mostly masses are quite heavy, for example the stars and the planets, this one is quite strong at that scale. So long range, weakest force in nature. So if we compare the strength of the force order wise, then the strongest force comes first, then the electromagnetic force, then the weak force, then the gravitational force. These forces act between the two bodies by the exchange of particles. So when one body applies force on another body, there is exchange of particles called as virtual particles between those two bodies. Now what are those particles? Let me clean the board, then I will write that. The exchange particle for strong nuclear force is gluon and the meson. So here it's a gluon or meson. For weak nuclear force, the exchange particles are W plus, W minus and Z0. As their sign shows here that this one is positive, this one is negative, this one is neutral. Electromagnetic force. The exchange particle in case of electromagnetic force is photon. The one which you see in case of gamma rays, or in case of light, or in case of electromagnetic waves. So these are the particles, photon, here written something like this. And in case of gravitational force, the idea is there must be particles which are mediating between the two bodies or two masses, but not yet verified experimentally. But the thought is they will be gravitons. But we are not going to discuss the gravitational force in case of Feynman diagram, because Feynman diagram is for subatomic particles. For example, between proton, neutron, electron, electron, and neutrino, any other particle. Please do remember this, because we are going to use them, especially this one and this one, the weak nuclear force and electromagnetic force, because they are very frequent. So to draw the Feynman diagram, one thing is very important, and that is time axis. And you are free to choose which axis you are taking as time axis, but the preferred way is to take the y-axis or the positive x-axis as time axis. You can choose either of the two. So if I'm taking time axis as x-axis, then whether it's a particle or antiparticle, they will always move forward in time. So particle or antiparticle, always move forward with time. So there is a convention to represent particle and antiparticle in case of Feynman diagram. As we have taken time axis along the positive x-axis, here this is time. So the particle, they are drawn with a forward arrow, something like this, and the antiparticles are drawn with a backward arrow. But this backward arrow doesn't mean that the antiparticle is traveling back in time. No. The antiparticle is traveling forward in time. Just to differentiate the particle and antiparticle, the arrows are drawn opposite to each other. So this one is for particle and this one is for anti-particle. Now the next thing, again I will draw the time axis here. If a particle emits an exchange particle, so the exchange particle will travel forward in time. It means it's emitted here. This is time axis. Now this particle is moving forward in time, this exchange particle. Exchange particles are most of the time they are represented by a wave or a dotted line. So both you can see in exam, do not get confused. So when an exchange particle is emitted, the momentum of the particle which is emitting the exchange particle will change. So you need to draw the path of the particle something like this. Now, when a particle receives the exchange particle, for example, let's say there is an electron which is receiving the exchange particle which is photon, then how you will represent it? So imagine this is time axis again, and here is an electron which is moving forward in time, and this electron is receiving a photon. When it's receiving a photon, it means that exchange particle which is photon, it was already traveling from somewhere and it's moving forward in time and it's going to hit the electron in future. So to represent this type of interaction, what we have to show, we have to show this exchange particle coming back from the past, meeting with the particle in future. Again, because this electron is receiving the incoming photon, the momentum of this electron will change and it will go something like this. Now, if you understood these two diagrams, then the drawing Feynman diagram will become very easy, because emitting will happen first and receiving will happen later on. So here you can draw or you can write here, this is emission of exchange particle, and here receiving the exchange particle. Now let me clean the board. So now let's see the interaction of two electrons with each other. We know two electrons, because they are like charges, they will repel. So how we can represent that interaction in the form of a Feynman diagram? Let's see here. So interaction of two electrons. You can draw that for proton as well, not a problem. But I'm drawing here for electron. So as you are free to choose which axis you want to take as a time axis, I'm taking time axis as x-axis. So imagine there are two electrons. One is moving like this and the another electron is moving like this. See how I'm drawing it. Both the electrons are moving forward in time. By mistake, if you in a flow, if you draw the other electron something like this, then the diagram will be wrong, because this shows that the electron is traveling back in time. Okay, you can draw this type of motion of electron if you have taken the time axis as y-axis, but do not draw here if the time axis is x-axis. So these are the two electrons, one electron here, another electron here, they are moving forward in time. Now once they will come close to each other, they will repel each other. How do they repel each other? So to show that repulsion, we have to show the exchange of particles between these two electrons. So any electron can emit a photon because this is an electromagnetic force, and you know, in case of electromagnetic force, the exchange particle is photon. So here, imagine this electron emits a photon, something like this. And what I'm doing here, I'm drawing the emission first, and then particle is moving forward, and in future the interaction with the another electron will take place. So that should be represented on the time axis. See how it's moving forward in time. So electron is moving here, and now it receives the photon. As it receives the photon, there will be change in momentum of this electron. And similarly, since this electron has emitted the photon, its momentum will also change. So now what you can see here, by the emission of a photon, their path changed. It means they repelled each other. Now in next, this was the first interaction. Let's take the next second interaction. And second interaction is, let's say, emission of beta plus from the nucleus. In case of beta plus, what happens here is a proton within the nucleus. There is a proton within the nucleus converts into neutron within the nucleus only. It doesn't go anywhere else. The proton is converting into neutron by emitting a positron. Along with the positron, a particle which is called as neutrino comes out. So two particles came out and proton converted into neutron. So let's show this interaction in the form of a Feynman diagram. So this is our time axis. Let's take a proton which is moving forward in time. Proton is moving something like this. Now what happens? This proton emits an exchange particle, something like this. So this proton emits an exchange particle, something like this. And when the exchange particle is emitted, the proton will convert into neutron. So now proton has converted into neutron. This exchange particle is a W plus. Why it's W plus? Because proton is giving out positive charge. And when it's giving out positive charge, it has to be carried by a particle which is of same charge. So this is W plus. Now this W plus has a short life. It means it will quickly decay into some other particle. This is a single particle here. It's a exchange particle and it's a single particle. So here what happens? Two particles are created. Out of this W plus, two particles are created, and those two particles are these two particles. One is beta plus and another one is the neutrino. Neutrino is particle. This is particle. And positron is antiparticle. Antiparticle, AP. So the arrow of positron should be denoted by a backward arrow, and the arrow of neutrino has to be denoted by a forward arrow. But again, as I said, this backward arrow doesn't mean the particle is moving back in time. It's just the notation of antiparticle. So after the emission of positron from the nucleus, let's see what will happen when an electron, which is beta minus particle, emitted from the nucleus. So here beta minus decay. So in case of beta minus decay, a neutron within the nucleus converts into proton. So this is the nucleus. This neutron is not going anywhere, it's staying within the nucleus, just converting into proton. So when neutron converts into proton, it has to give out something. And what is that something? That something is a electron, which we call beta minus particle. This beta minus is not alone. It's the antineutrino which is emitted along with this beta minus particle or along with this electron. So in this process also, two particles are coming out from the nucleus. One is particle. Now here electron is particle. Earlier the positron was antiparticle, and this antineutrino, the name itself suggests this is antiparticle. Let's draw the Feynman diagram for this beta minus decay. And just to show you, this time I'm taking the time axis on y-axis. So this is the time axis. Time. Now time is going upward. Earlier it was not like it was going horizontally. Time was just represented. Okay, time always moves forward. So time is just drawn upward. So the motion of particle should be towards the future. So imagine there is a neutron which is going like this. This is neutron. This neutron emits an exchange particle. It emits an exchange particle. When it emits an exchange particle, it converts into a proton. Now what is this exchange particle? What is the nature of this exchange particle? This exchange particle, because electron is emitting the beta minus particle, it should be negative in nature. So this is W minus. This W minus, again like W plus, has a short life. So this W minus will quickly decay into a particle and antiparticle pair. So here is this. Now one will be electron, another one would be antineutrino. As antineutrino is antiparticle, so you may have guessed the arrow for antineutrino should point backward or downward, and the arrow for particle, which is electron, should point forward. So still you can see these two particles, they are still moving forward in time. if you just draw their position on time axis, so initially they are emitted, now here they are moving forward in time. So we saw three diagrams for Feynman diagram. One for interaction of electron, one for emission of beta plus from the nucleus, and the third one, the emission of beta minus from the nucleus. In next video, we will draw few more diagrams related to Feynman diagram. Till then, keep practicing from your textbook. Textbooks are really good. You should read it because you are very close to writing your final exam. Keep revising, keep practicing. Always aim higher than the expected. So if you like the video, please hit the like and subscribe button and share with others. Thank you. See you in the next class.